Hello everyone and welcome to the channel. In this video we are going to dive into a powerful tool used extensively in fluid mechanics and beyond, Einstein Summation Notation or ESN. If you will be following along with our future videos on the mathematics behind fluid flow, understanding ESN is crucial. So, why bother with Einstein Summation Notation? Well, as you start dealing with more complex equations in fluid mechanics, especially those involving tensors, things can get messy very quickly with all the summation symbols. ESN provides a way to simplify these expressions, making them much more manageable. This is a huge benefit when you are working through lengthy derivations or implementing those equations computationally. It also offers a more transparent way to represent operations with different types of tensors, from simple scalars like pressure to more complex entities like the stress tensors or fluid velocity gradients. The core idea behind ESN is the principle of automatic summation. Whenever you see an index repeated within the same term of an equation, it automatically means we are summing over all possible values of that index. This repeated index is referred to as a bound or dummy index because its specific value doesn't actually affect the final result. It's just a placeholder for the summation. Look at this simple example, AI by I. This concise notation is equivalent to writing out the full sum over all possible values of I. This becomes incredibly useful when dealing with more complex expressions, saving you a lot of writing and making the equation easier to read. Now, it's important to distinguish between two types of indices in ESN, bound indices and free indices. As we just discussed, bound indices are those that appear twice in a term and we automatically sum over them. After performing the summation, these bound indices effectively disappear from the resulting expression. Let's look at this example. Cik equals to Aij bjk. Here, the index j appears twice, so we sum over it. The resulting tensor C will have indices I and k. On the other hand, free indices appears only once in a term. These indices are not summed over and are crucial for understanding the dimensions of the resulting tensor. A key rule is that the free indices must be consistent on both sides of an equation. Next, let's introduce a very useful tool in tensor algebra and ESN, the Kronecker delta, denoted by delta ij. This is a special second-order tensor that essentially acts like an index replacer. It's defined as being equal to 1 when two indices are the same and 0 when they are different. For example, delta 11 is 1, while delta 12 is 0. A useful property is that if you have a bound index paired with a Kronecker delta, like Aj delta Ji, the Kronecker delta effectively selects the component where the indices match, resulting in Ai. You can think of the Kronecker delta as the identity matrix in tensor form, which you can see in its matrix representation in 3D space. Finally, let's briefly touch upon the Levi-Civita symbol denoted by epsilon ijk. This is an antisymmetric third-order tensor, meaning that if you swap any two indices, the sign of the symbol changes. It's primarily used to express operations like vector cross product and curl in a compact form. The Levi-Civita symbol is defined based on whether the indices form an even or odd permutation of 1 to 3, or if any indices are repeated, in which case it's 0. This antisymmetry property is crucial for simplifying expressions. For example, the cross product of two vectors a and b can be elegantly written using the Levi-Civita symbol as Ci equals to epsilon ijk ai bk. To help solidify your understanding of how tensor orders are represented in Einstein Summation Notation, let's take a look at the following table. It gives you a quick overview of different tensor orders and how they are expressed using ESN. A scalar, which is a single value, has an order of 0 and requires no indices. Examples include pressure or temperature. A vector, representing a quantity with magnitude and direction, has an order of 1 and is denoted with a single index, like Vi for a velocity vector. A matrix or a second-order tensor has the two indices, such as sigma ij for stress tensor. Third-order tensors have three indices. A good example is the Levi-Civita symbol we spoke about earlier, epsilon ijk. And finally, a fourth-order tensors have four indices, like C, ijkl, often used when describing material properties such as elasticity. Understanding these representations is crucial for working with complex fluid mechanics equations. As we progress, we will see how ESN simplifies these representations, making our calculations much more efficient. So, to recap, we have learned that Einstein Summation Notation is a powerful tool for simplifying complex mathematical expressions, especially when dealing with tensors. We have covered the key concepts of bound and free indices and briefly introduced the Kronecker delta and Levi-Civita symbol, which you will encounter frequently. In our next video, we will start putting this knowledge into practice by applying ESN to some fundamental equations in fluid mechanics. Make sure to subscribe so you don't miss it, and feel free to leave any questions in the comments below. Thanks for watching.